So good morning everybody and welcome to one of the first sessions, 3DUI 1, a whole series of 3DUI sessions. I'm Daniel Zelasko, I'm your session chair and will guide you through the session. Without further ado, I want to point out to the first paper in the session that is also nominated, one of the nominees for the best paper. Which is GlanXR, a hands-free, fast switching system for virtual screens. And Zhao will present the talk. Thank you very much.
Okay, hello everyone. I'm Guanghan Zhao, and today I'm here to present our work, GlanXR, a hands-free fast switching system for virtual screens. So let's get started. So first about the research background of this work. So with the advancement of XR technologies, head-mounted displays have become powerful tools to enable multiple large virtual screens for the users to work with their tasks. However, to navigate and operate across these screens remains a big challenge. Current solutions like icon clicking and multi-screen approaches disrupt workflow and also cause physical strain due to frequent hand movements and the weight of HMDs. On the other hand, the rise of gaze-based interactions offer a potential hands-free solution, but the accuracy issues can hinder the effectiveness, leading to a reliance on slower compensatory mechanisms like dwelling or pursuit. So for our system, in order to trigger a successful screen switch, first the user have to look at a thumbnail for select. So here are the thumbnails surrounding the view. And then the gaze must be fixated, and meanwhile the user's head should rotate to the opposite direction of the gaze. And at the same time, the eye head position stays beyond the threshold, here's the threshold, range for over 150 milliseconds. After the head is rotated, then the new screen can be switched. So what's the eye head position threshold range? Here is the thing. So we developed this adaptive eye head position threshold range with two halves of ellipses on top of each other here. So based on the results of previous works, we know that the limitation of eye head position of human eyes are the averagely 28 degrees on the top and 47 degrees on the bottom and 44 degrees on the left and right. And with the equation of ellipse and applying two temporal multipliers, Kp and Kn, we have the equations to calculate the two halves of ellipses here and here. Additionally, we compute the threshold values with a root mean square method with a 30-second time window. And with this method and along with the algorithms that we talk about the two halves of ellipses, we can make the system to be sensitive to the magnitude of values, make it effective for capturing different kinds of variations in the real-time datasets. Also, the system imparts a smoothing effect, enhancing the stability of the analysis and facilitating the identification of overarching trends within the real-time data. And it can dynamically adapt to the user's real-time eye gaze data, and the eyes are not required to rotate to far positions from their eyes, and therefore mitigates the potential eye fatigue. The algorithm can able to automatically adjust the threshold range in varying situations. As we can see, this image is the initial shape of our threshold range, and with the eye gaze data is adding to the data set, we can adjust the threshold range in real time based on the gaze data, and it can correlate it to the different content layouts and like adjust the shape to like different shapes. So next is about our peripheral interface. We developed those thumbnails here, as we can see from the previous slides, and this, like for this, the screen material is like captured by the main cameras, like post-processed using a shader script. And then the thumbnails are initially positioned within a range of 35 degrees here, like from the center, to 55 degrees, like to the edge of the field of view. And each thumbnail has a field range of 60 degrees. And please note that this number can be changed for adding additional thumbnails. We use 4 is just because it's simple to test, and also based on the previous demonstrations, we know that the 4 thumbnails is enough for daily usage of interaction. And the thumbnails are designed to be semi-transparent with soft edges to mitigate the potential disruption to the users. So please take a look at this image. The purple area here, the purple rectangle, stands for the preview material, which was sampled from the pixels of the different screen materials. And from those preview materials, we clip them into a thumbnail, like here, this blue area, a radio shape area, yeah. And in order to make the thumbnail to move and also like resize in real time based on the eye gaze data, we calculate the size and position of the preview material with the following equations. So this video shows how the threshold range adjusts itself based on the real-time data. Please note that this yellow dot here stands for the eye head position, and also like when the gaze is like surpassing the threshold range, the thumbnail will be locked and activated. The next part of this video shows the user is like using our system to navigate between crossing the different screens. As we can see from the video, he can like switch between screens in a rapid but also robust way. About our experimental design, we applied 2 different scenarios: a fast switching scenario and a working simulation scenario. So for the fast switching scenario, we make the participants to switch between the screens in a fast manner, and the task was to click on buttons. These buttons are randomly assigned and attached to all those screens, and the participants have to like click on them rapidly. And for the working simulation scenario, we were trying to simulate a real working situation, and the task was to fill in a form. Therefore, they have to click on the buttons and type some text while switching between the screens. And there are 4 conditions applied in our experiment. The first one is the baseline condition, like the task bar we use every day. And the second one is expensive multi-screen. The third one is gaze selection method. And the last one is our GlanXR. From the fast switching scenario, the results showed that participants could rotate and switch to the target screen more precisely with the baseline method and our approach. And GlanXR enabled a more natural, fast-facing head posture, but led to a larger eye movement amplitudes. Lastly, participants experienced greater neck strain with the expansive multi-screen layout compared to the baseline condition. In the working simulation scenario, we found that the 4 methods did not impact task completion speed, and the participants were able to locate and switch to the target screen more accurately using both the baseline method and our approach compared to the other methods, and this result is in line with the last scenario. Last one, participants experienced more stress in their necks when using the multi-screen method compared to baseline and our approach. We also tested the range of eye head position in our experiment, and we found the natural distribution range of eye head positions are approximately 25 degrees on the left, right, and top sides, and 35 degrees on the bottom side. And this result is in line with the demonstration by Sandemark and Gellerson in their work. So as a conclusion, the contribution of this work are first the design and implementation of an adaptive hands-free screen switching method that offers unique advantages, and an experiment evaluating the different hands-free methods against the baseline and for those metrics like performance and head rotation, addressing the gap in previous works. And lastly, investigation and analysis of natural ranges of users' eye head position, adding to the body of knowledge of gaze interaction techniques. Okay, so that's all. Thank you for listening. If you have any questions, please feel free to ask.
Are there any questions? I think we have time for a few. Otherwise, let's start me with one. So in the paper, you are saying that you placed the surface of the screens 1 meter in front of the user, correct?
Yeah.
Is there any rationale to that? So have you considered the focal distance or any other reason why 1 meter exactly?
Actually, 1 meter is like just by some logical test, like usually how far I place my screen ahead, but that 1 meter distance is like fixed. Based on that 1 meter, we designed the size of the expansive multi-screen layout as we can see here. So we were trying to make all of them like in the field of view at the same time, but meanwhile, like don't make them looks like in a different size. Although in this image it looks a different size, but when the user is experiencing this environment, all of them looks the same size in the same distance.
Yeah, thank you. Any other question? No, there's one. I'll come with the mic.
This is just a bit of a thought question. Have you thought about using this for, instead of screens, but 3D navigation?
I had this thought, like after I finished this work, I thought about that. I was considering about if I'm gonna do that as my next work. Honestly, yes.
But what are your thoughts? I mean, what direction do you think you'll go in?
I was thinking like use this method to navigate through the virtual environments. Use it as a trigger of locomotion. So for this method, the user have to stare at a thumbnail to select. So I was thinking maybe I can like change these thumbnails into like buttons to go forward, go backward, turn left and right. And when they want to trigger this actions, they have to focus on the periphery area of their eyes. Therefore, they don't feel that much vection when they are actually like locomoting. So maybe like by using this a hands-free method for locomotion, maybe it will like solve the motion sickness problem at the same time. So that's what I expected.
Sounds very interesting. Thank you very much.
Thank you.
Thank you. Any other question? Last one. Maybe I have one. In the discussion, you were commenting on in the working condition, the different condition in the working task, the conditions not really differing a lot, and concluding that your GlanXR method is maybe comparable, which basically makes you accepting the null hypothesis. So have you any comments on the power of the experiment and this test?
Sorry, I don't like really get your question, but you mean like for...
In the discussion, you were basically saying that all the conditions did the same in the working environment, and I was just wondering how the power of the experiment looked like. So get an impression if that really is true.
No, as we can see here, we have a lot of like significance. It's not like exactly the same through all the conditions, but only for, we were trying to emphasize like for the completion time, there's no significant difference. And from that, we know that our method will not like affect the task completion speed. Like they all have the same speed. So you know what I mean, right? It's not for everything.
Yeah, I know what you mean. I just don't completely agree on the statistics here, but yeah, I think this brings us to the end of the talk. Yeah, thank you again.
Thank you.
Okay, then I'm happy to announce the second talk in this session, which is Whirling interface, hand-based motion, matching, selection for small target on XR displays. And the presentation will be done by Hyung-il Lee. Thank you. Great.
Okay. Can I hold it? Okay, hello. I'm Juyoung from KAIS, and I will introduce the Whirling interface. Is about the hand-based motion matching selection for smart target on XR displays. Wait a bit. Okay. So this work is a collaboration of 3 different institutions and is advised by the Woontack group. So, where's my cursor? So during all talk, you can check the slide with the QR code, so please check on that one. So let's talk about the paper. So our goal is developing a target selection interface suitable for daily use. And this is the sum up, and we'll introduce the Whirling interface. It is a version of the improved interactivity with a consistent performance, and we also include the experiment with the comparing with the raycasting, and we'll sum up with some discussion. And I hope all you guys attend the keynote, and I feel that it's perfect fit with the keynote. Thank you to attend. So let's start from the devices. So all we know is immersive headsets are already here. But today, we'll more focus about the lightweight smart glasses. Also, there's several lightweight smart glasses in commercial devices, but they have not that good hand tracking, motion tracking, or maybe they only have few camera sensors or something. So we'll focus on that one. So our goal is creating an interface for daily use AR. So what is important for the daily use AR? So also the banker told something, but now we'll focus on the smart target. Why smart target? Because we don't want to make some abstraction on the real world. We want to see the real world and see the contents on it. We don't want to hide that. That's why we need the smart target. And the second, bare hand, already we knew hand is important, but as hand is most common. Really. So there's several research who do for some kind of small target selection with a bare hand, and these are all common three list. So first, the ray casting is the most common method, and eye gaze. We all love eye gaze, and it is intuitive and is of use. And also, there's many research using multimodal and multi-step to complement the limitation of each other's. But all these has some challenges. For first, ray casting, it is highly dependent on tracking. So it require more IR camera, or it needs really precise to make the input, and also it needs some confirmation gesture, and that part some people got difficulties. And for the eye gaze pointing, it's almost same as a ray casting with the hand. It also dependent on the tracking, and also it requires confirmation gesture. And also there are some issues on the tracking issues on the outdoors. And multi-step, multimodal, these are really good in some context with the immersive one, but actually we requires more attention and we need more training. So we started our idea with the motion matching based selection. I'm not sure all knows about this or not, but actually this is not a new idea. Is about 10 years. So first appeared in the US 15. So it's about, they use the gaze-based gaze to follow the orbit to select target. And also there was one paper using the hand to select target on the TV screen. And actually these succeed to make an input for the smart target selection. But also recently there was one paper also used touch screen gesture, which is more reliable than eye tracking or hand. And they succeed more accurate and solve the scalability issues on selecting. So we'll start from here. So they show the potential. So we choose the reliable modality using the hand motion and targeting the smart target selection. But there are still areas for improvement because they're all focusing on the input detection itself. So they don't have the interaction features like feedback of doing well or bad, and also some kind of confirmation or cancellation function as all ray casting has. And also they missed some, there was no study about the comparing with the current method like ray casting. So user can feel the difficulty, or maybe system can be difficulty. So we will focus on that one. So details are in our paper, and I will just introduce the important improvement from our system from the motion matching based selection. So we align with the Dornum's principle, following have to make a feedback and doing well and confirmation and cancellation feature. So first we implement the real-time feedback. So we choose to use adaptive time window to get the real-time feedback to them to tell them doing well or not. And the left figure is showing the adaptive time window, how it works. So we can get the direct feedback every second. And second, we add some input state to activate the confirmation and cancellation. So all these systems are activated by correlation coefficient and root mean square and some thresholding. So the details are in the paper. So it's difficult to see how it works, so maybe I can just show how it works. It looks like I can select like this. Or maybe I can select the right one. Actually, it's difficult to test with the. So I can cancel like this one too. Okay, select it. So you can also try the demo, and the QR code is on the web. So please try. So now I think all you guys understood how it works. And now I will go to the experiment section. So we tested with the 16 right-handed participants because we only use the right hand. And our study design was a 2x2 within subject design, and we tested with 2 different distance and 2 different methods. And we use device as a Microsoft HoloLens too, because it has a wide field for the hand tracking and it is AR. And the target condition was we used 12 target and showed as a 4x3 grid, and is a size of 48 millimeter of diameter, and it was placed in 1 meter far and 2 meter far. And the walling condition was setting with the 2 different speed, 2 different direction, and 3 different phase, and it resulted to 12 settings. And for the procedure, we all separate each subject design for different sessions. So we have 4 sessions, and each session has a 48 trials for 4 repetition of the target selection. Yeah. So this is the results for the success rate. We can check that the ray casting far was the worst and others was comparable. And for the completion time, the far condition was with the ray casting was worse also, but actually Whirling shows quite consistent performance across the distances. So actually distance doesn't affect the quality of the input for the Whirling. That was the thing. And maybe you guys can think like Whirling can be a bit difficult but actually people doesn't feel that. And for the raw TLX test, the workload, the ray casting far was the worst and the other was comparable. So then maybe we can check if the placement affect the performance, and we can see here is the heat map of the different placement. It is right aligned to the real display view, and you can check that and this is completion time. So here we can see the Whirling showed consistent performance across placement, but ray casting is with lower performance, especially for the corner. Actually, this can be due to the fits low because it's not at the sphere condition. And then also we want to check about one more thing in aspect of the system. So we calculate the sensing FOV with the required sensing field of view of the when making field, and we recorded the last 3 seconds of the making input until making input, because we asked them to start from the hand down to up, so we remove previous one because that makes big difference. And for the sensing field of view, we can check that Whirling has really requires smaller sensing field of view than ray casting. And this is the right side one is displaying the hand position of each participant when they do the Whirling. We can check everyone can do quite in the consistent position, even they are targeting different positions target. So we can say the Whirling can be one possible solution for low sensing field of view glasses. So it's wrapping up the talk with showing the findings. So I summarize with the 2 big findings from our work. So first, Whirling has better interactivity. Actually, also for the qualitative results, they shows the Whirling's feedback was better than the ray casting, because ray casting we have self-feedback, but they didn't know why it doesn't work and why it works well in some times. Because it is highly dependent on the tracking, and the finger is more difficult to tracking maybe. And also cancellation feature was crucial. So we allowed to try multiple times until 15 seconds for both ray casting and Whirling. And for the walling, 18% of trial needed multiple attempts, but actually, including cancellation, even walling was faster than raycasting for the distant target, and also it required less task load than raycasting. So cancellation was not that difficult, we can say that. And for the advantage of sensing, we could get the consistent performance. So we can say it requires smaller sensing field of view, and also it is better for self-occlusion problem. And we can say it has some potential for less accurate sensors, like using IMU or radar or maybe EMG. Yeah, okay. So for the application, we can integrate and with current, or maybe try with others. But still, we have some limitation. We need to we don't have, we can test with the improved technique like raycasting with the intentional aware, or maybe we also have to address the scalability issues, and we have to test with the diverse scenario like mobile, outdoor, or working, or multitasking or something, and maybe in others. So this is summary of the whole talk, and thank you for listening.
Thank you very much. Same procedure. Any questions from the audience? I'm coming. Give me a second.
Hello, Michele Fiorentino from Polytechnic University of Bari, Italy. It's very interesting, this interface is very innovative. Maybe I lost one part of how many targets you can address maximum, so that's how it scale up, so basically.
Yeah. So here we test with the 12 target, but we, in the paper, not our paper, but we cited, they use the touch screen and they succeed to scale up to 30 to 40 and 50. So we believe we can scale up for that one. But here we start for small target numbers. So we can just say 12 is enough for now, but I believe it can extend, and it will be included to our next work. Thank you.
Maybe just to have a, how robust is maybe next works, to see how scale up and how robust robustness changes with the number of
yes,
of
that's possible.
Okay, because I see a problem when the targets become more than 20 or.
Yeah. And actually, why we choose 12 targets is because we just check the number of targets from the home screen of the HoloLens and home screens of CAS, and actually they all have less than 12 targets in the one screen, so that's why we choose the 12 at the first position. So we need at least 12 if we want to work on something. So if we cannot scale up, maybe we can use as a widget and as a substitute interaction method too. Yeah, we are thinking
12
about
is a reasonable number. Okay,
Yeah,
thanks.
thank you.
Bruce Thomas, University of South Australia. I guess the question is, in the experimental design, why didn't you just do a traditional Fitts law study? And the second question is, and I think it's a follow-on for this, how close can your targets be? Because my concern is when you're doing this to circle it, you're going to grab multiple targets if they're clustered together.
Oh, no. Every target has different target speed or phase or the direction. So everyone has different target movement.
Oh, okay.
Yeah. Every target has different target movement, and then why we don't choose to do the Fitts law style, because actually when so we were more target. So actually, it could be a good option if we follow the Fitts law, but actually we want to test to place the button in the whole scene of view of the display for the smart glasses, because we want to put some target in the corner, because usually the HoloLens or others has some difficulties on selection on target on the corner because of the tracking issues. But actually, maybe we can do more precise Fitts law test for the next time. But actually, what we found from here is the target size doesn't matter. Even for the walling, the far one, the success rate or completion doesn't go also up. Actually, it was stable. So yeah, you're true. We have to, so one of our future work is we want to find some kind of difficulty index of the Whirling. Yeah.
Okay, thank you.
Okay, thank you. When there are more questions, and I think that's true for all the authors, please approach them after the talk or the whole week, and let's thank the authors again. So the next talk is about object speed control with signed distance field for distant mid-air object manipulation in virtual reality, and the talk is given by Wolfgang Stuerzlinger.
All right. Thanks for the introduction. So I'm giving my talk on behalf of my co-authors, both of Mucahit and Ufuk, both of who can't be here today because of visa issues. Yeah. So the work we did concerns a mid-air interaction with distance objects. So imagine that we all familiar that we can grab an object in mid-air directly in front of us, but that's limiting because not every object is within arm's reach. Now we can navigate there, but that comes with different trade-offs because you need to get there and come back potentially. So we want to interact at a distance. So assume that I have some objects over there in a distance and I want to interact with them, and the problem becomes, well, I can interact with them, but they're far away, so there's a speed accuracy trade-off associated with that because they're small or they're distant, right? I mean, these problems. And all of these inaccuracies, or the tracking system has problems, right? All of these inaccuracies affect the manipulation and thus also the user experience. The big idea in this talk is to use a signed distance field to improve the manipulation. I'll talk more about the details in a few minutes, but with the intent to increase the accuracy, improve the accuracy, and reduce the error rates, just to make it easier for people to do manipulation tasks. Previous work well known in this area is, of course, raycasting and the Gogo and Homer techniques, which are all targeting the manipulation of distant objects. And let's see if this works. Yes. So I mean, the raycasting is like with a laser pointer that you point at a distant object, and okay, now I'm selecting this speaker, and now click on it and move it somewhere else, type of thing. Right? Now, inherently to all manipulation tasks is that as you do things faster, you make more errors. On the other hand, you want to be as fast as possible, and every human doesn't want to waste time, type of thing. So you have a natural balance here between speed and accuracy, and Fitz's law and so on has explored that at depth, and I've done quite a bit of work on that. Still, and one of the things I want you to think about is that humans are actually fairly cognizant about the speed accuracy trade-off, right? If you ask people to go faster, they notice that they do more errors. And if you ask people to be more accurate, they notice that they take more time. So there's this kind of natural valley that you fall into. That valley is, of course, different for every person, but in general, there is somewhere a minimum where people go like, okay, that's where I'm comfortable to interact. On the technical side, the signed distance field represents shapes in a continuous space. So instead of having the edges of the object be continuous, we can basically think of something like a wave that emits from an object. So the simple thing to think about is for a point, the signed distance field is a series of spheres, right? And for any object at a large distance, it's also a series of spheres. But for closer objects, the distance field kind of follows the contours of the object. It's a simpler explanation of how assigned distance field works. In 2D, it's often easier to visualize. In 3D, it's more complicated because there's more intricacies in the 3Ds. But in essence, it encodes the minimum distance from any point in space to a shaped surface. So if I have this point right in between here, this is a little bit closer to the laptop, and if it's over here, then it's a little bit closer to the microphone stand, and so that will be the minimum distance here or the minimum distance here. And so at any point, and you get these nice ridges in there where you have equidistant two objects. Now, because we are faced with distant object manipulation, the issue that we have an increased control display ratio, right? It's really hard for me to hold the laser pointer steady here, right? I mean, you can see the little bit of jitter, and this is just hand jitter here, right? I mean, now I didn't say anything about the tracking system because we also may have a tracking system, and any inaccuracy in the rotation will also add jitter to this, right? So we have multiple sources of jitter that make this task difficult at a distance. And at a distance, we also have the problem that we have potentially reduced depth cues, because once we get beyond 3 or 10 meters, in particular, stereo cues just fall off very quickly, and stereo does not add much value at that distance. Now, if we now use this assigned distance field to find how close these objects are, can we control the speed accordingly? And does that work, and does that provide benefits? And that's actually what we're investigating in this work is, does the SDF increase the accuracy and improve the user experience? So what we did here is we created some tasks where people have to go either through a series of rings or tora, or follow a wire in kind of like the normal buzz wire task, or follow a very complicated wire where you have to take this ring and move this along the wire. For this purpose, we created a assigned distance field around the object, so around the obstacles, and with 1 centimeter resolution in Unity, and computed the SDF for each point in that volume. And when we have now our controlled object, in this case this ring, we can compute for every point on the ring, we can compute how far away it is from every surface of the object and so on very quickly. It's a lookup in the SDF, and we can compute the minimum value here. And then the idea is, once we know the minimum value, we can now say, well, if we get too close to the microphone, say we have this big ring here and we get closer to the microphone, we actually slow things down. Now I'll show you a video of this in action. This is out without the assigned distance field. In this case, you can see that we show the user a little bit where they have to drive this cube towards with a path, and the red corners on the cube are collisions, right? And so with assigned distance field, once you get closer to the object, the object naturally slows down. And you can see also we show here, and this is not shown to the user during the experiments, this is just debugging visualization, right? That we can have the closest feature and everything identified. And that green bar shows you how much we slow down the user when they manipulate objects here. But they saw the hit counter, so they saw how frequently they hit. So they got some feedback how accurately they were doing. So this is a task that has been explored in previous work, the buzzwire task, and it's fairly complicated, but it's not that challenging per se, because depending on the spacing of the wires and the wave, you actually have enough space to move through here, and it gets easier. But it still gets easier with the assigned distance field. how this task is the most complicated task, and one of the issues that's introduced here is that at positions like this one, the closest point can actually be on the other side of the ring, right? So there's actually situations when there's like 2 or 3 closest points, and that's when it gets really difficult to control the ring and make sure you don't hit any of them. And sometimes watching participants do the task is painful because you're going like, yes. Like this episode here, right? There where they banged the ring multiple times against things. But eventually they fulfill the task. And it's actually interesting, one of the things that happens frequently is that at the very end, they still one more time hit just because they accelerate at the end, right? So here you see the closest points jumping multiple times between different surfaces, and that's an indication that this is a really difficult pass, piece of the wire where you have to be very careful with controlling how you manipulate the object along the ring here. And as natural, you know, as people do this, they get better with this. So this is not necessarily super typical performance. You know, after repetitions, you get better with this. So we did an experiment with 18 participants, the 3 tasks that I already showed, within participants design with 2 techniques, either just standard raycasting where the object is basically on a long stick in essence, and raycasting with the signed distance field. And we measured the time and number of hits, and also investigated the user experience through NASA TLX and the questionnaires. And so for brevity, I'm only talking about significant results. We observe a lower error rate without slowing down the users for task 2 and 3. For task 1, we basically have no results. The task is basically too easy, if you wish. But what we do see is clearly that with the signed distance field for more complicated tasks, clearly reduces the number of errors and also the number of hits, right, that we're using. And also in the questionnaires, we got a better usability rating for the signed distance field technique from the SUS, this simple usability. I got the acronym wrong. SOS questionnaire, we basically got a good grade for the interaction instead of a D, which was naive raycasting. In the NASA TLX, we got nice results also for mental demand and temporal demand and frustration, where the SDF is always better. For the task 2, we also got better rating for performance and overall task load. For the task 3, which was the most difficult, the physical demand also decreased, the rating decreased. But that's a little less consistent, so we can't claim that this holds overall. So for simple tasks, signed distance field doesn't matter. It doesn't hurt, but it also doesn't improve things. For complex tasks, we observe that the signed distance field reduces the error rates without slowing down the user, so it's overall beneficial. And the usability from the users also rated better. So generally speaking, if it's necessary that you that you have no collision, using a signed distance field once the task gets more complex is a good idea, and that clearly improves the user interaction. So if you have any further questions, you can also talk to me after the talk, or contact the co-authors. Mucahit has put his QR code up here for an email, and thank you for your attention.
Yeah, thank you very much. I'm already going. Bruce was first, and you're second.
I'll yield to you first. Great talk. I like that this is an incremental improvement on an existing, you can add it or delete it. Could you describe how you picked the length of your ray, and what's the impact of the length of the ray on the technique?
Absolutely, thank you. So we picked the length of the ray to kind of hit multiple criteria, right? I mean, if we made it so that people could reach it, then why would they use a ray, right? Why would they use a ray? So it had to be long enough to be far away. On the other hand, you still wanted some benefit from depth perception. So that was basically the trade-off that we looked at in terms of the length of the ray, right? Because if I go, say, 10 meters out, right, depth perception kicks out, and then I'm relying only on occlusion cues and so on. So we try to keep that as a balance. Does that make sense?
Yeah, but also how does it, if it's too short, you're not getting any benefits because it's attached to your hand.
Yeah.
But if it's too far away, then it's getting really wobbly.
And that's the other consideration, but we were actually also thinking about seeing, right? I mean, one of the issues is if you manipulate an object at 10 meters distance, seeing exactly if the ring is not big enough, seeing how close it is relative to the wire, it gets more and more difficult because your depth cues get reduced further and further, right? The further away you are. At the same size of object, right? I mean, of course I can make the object bigger and then then it doesn't matter how far away it is, right? I mean, I can go that way too, right?
Would it be correct to say this is a good technique for something that's just out of arm's reach? Kind of a minimum?
I would say yes, you're correct. In the sense, somewhere between out of arm's reach to, I guess, about 10 meters would be the best way to say it, right? So room size type of thing, right? Not this room, but normal room size is a good range, I would say, right?
Sorry, I'm dominating.
Huh?
I'm talking too much.
Yeah. Hey Wolfgang, great talk. I was wondering, does the technique somehow influence tool embodiment and agency, like negatively, or I don't assume positively, but
We didn't look at that, okay?
from personal experience, maybe testing it.
That's what I'm just switching to. It does and it doesn't, because it slows you down, and some people notice that more than others, okay? So that's the issue, right? Some people naturally slow down, and the technique just slows them down a little further, and for them it's so gradual that they almost don't notice it. And some people strongly notice it, okay? Because they're just less careful, okay? So I cannot give you a better answer than that. Does that make sense? Yeah, it's a good answer.
Okay, I think that's it. Further questions, please, after the session. We have to continue, and let's thank Wolfgang again. Yeah, this brings us to the last talk of the session, which is Push to AR, Enhancing Mobilist Interactions Using Augmented Reality, and Jonathan Wieland will present.
Okay, thanks a lot for the introduction. As already said, my name is Jonathan Wieland. I'm a PhD student with the HCI group at the University of Konstanz in Germany. And during my research stay at Carnegie Mellon University in David Lindelbauer's lab, we developed a novel interaction concept called Push-to-AR, which I'm really excited to present to you today. So when you pull out your phone and look at the different apps you use on a daily basis, you will notice that they have one thing in common. So most of them rely on scroll lists. And the reason for that is, of course, the limited screen space these mobile devices offer. So while these lists are great for giving us quick access to potentially endless data, despite the small screen, they also come with challenges in navigation and orientation. So users often lose track of their position in these lists and struggle to efficiently access, compare, and filter items of interest. So for example, the user here in the video, which is me, by the way, might come across a movie he's interested in while browsing a list online. But as he continues scrolling and exploring the page, it becomes harder and harder to locate that movie again. To address these challenges, we propose Push-to-AR, which extends the phone screen with an AR headset and provides users with the option to push items into the additional AR space to allow for bookmarking and easier comparisons. And by the way, all the videos and photos of our prototype I'll show today were recorded using the Vario XR4 headset. Our technique builds on three concepts that have been proposed by prior research. So firstly, works, for example, by Olsen or Alexander, introduced different types of scroll indicators, like shortcuts and visual thumbnails, to help users navigating long lists. and also quickly return to important items. Other researchers, such as Normand and McGuffin, proposed virtually extended screen-aligned displays, which extend mobile screen space into augmented reality, providing users with more screen real estate. And finally, Wu et al. And Hartmann et al. Explored the idea of pushing and pulling content between devices or realities. And with push to AR, we combine and extend all three of these concepts. So how does it work? Basically, with our technique, users simply perform a right swipe on a list item of any web page to push the item to the AR space adjacent to their phone. And items that are pushed to AR are highlighted with a randomly assigned pastel color and visually connected via lines to scroll indicators in the browser's scroll bar. To remove an item from AR again, users need to perform a left swipe on it, and as you can see in the video, the item then just disappears. Scroll positions of items on the phone and their AR counterpart are synchronized. So as you can see here in the video, while the user scrolls up the page on the phone, also the items in AR move up accordingly. And for items that are no longer within the smartphone's viewport, the AR representations are stacked and gradually moved behind each other to keep them in the field of view of the AR headset. Users can also tap on scroll indicators to quickly scroll to the corresponding item on the screen, as you can see here in the video. And with these features, we think that push to AR allows users to easily collect, compare, and filter items from a list to find the item that best fits their needs. We built push to AR as an open source browser extension that can be directly added to the browser on your phone. And this extension allows us to inject our own code into any website. And when you swipe right on a list item, the extension then scans the web page and tries to identifies the list item. And once the item is identified, we use the browser's API to extract details like the element's height, position, or also the URL of the item. This information is then sent to a Colibri server, which manages the communication between the phone and the AR headset, ensuring real-time synchronization between the two devices. The AR headset runs an application we developed using Unity 3D. And finally, once the AR app receives the link of the list item you swiped on, it retrieves metadata such as the image, title, and description using Open Graph from the website and reconstructs the list item in AR. And on the phone, of course, we also track events like scrolling and continuously update the item and viewport positions so that the AR display stays synchronized with the phone screen. For tracking, we use an HTC Vive Tracker 3.0 to accurately track the phone's position and also keep the AR display aligned in real time. While inside-out tracking from the phone would potentially also be possible, our pre-test showed that issues with accuracy and drift, because of that, was just not accurate enough to use it. And we wanted to really evaluate the full potential of our technique with ideal tracking. To evaluate push to AR, we conducted a user study with 16 participants in which we compared it with the standard non-AR phone interface. And as shown in the video, participants completed a shopping task in a simulated online store, and this store included 36 items across 3 different categories. Each item had a price and a star rating between 1 and 5, and participants' task was to identify the 3 cheapest items in each category with at least a 3-star rating and add these 9 items to the shopping cart. We evaluated participants' user experience through the user experience questionnaire, a concluding interview, and also asked them about their overall preference. We also measured workload using the NASA TLX, and finally we assessed performance based on task completion time, error rate, and the number of interaction steps required to solve the task. And as you can see here, participants clearly preferred push to AR over the phone condition. So in fact, 15 out of 16 participants indicated that push to AR was their preferred choice for solving the task. This preference was further confirmed by the user experience questionnaire, where push to AR received significantly higher ratings across all measured dimensions. Statements during the concluding interview provide further insights regarding participants' experiences. So for the phone condition, participants, in this case 6, mainly valued the high familiarity with this very common interface. But they also reported that they perceived a much higher mental load with this condition when solving the task. And they also expressed like general negative sentiments such as being restrictive, tedious, or frustrating. For push-to-AR, participants mainly valued that it allowed to display relevant list items simultaneously, and they expressed general positive sentiments such as being helpful, cool, or less tedious. However, some also said that the technique needs some time to get used to. Yeah, the higher mental load participants indicated to perceive with the phone condition was also confirmed by the NASA TLX scores. So overall, participants perceived significantly less workload with push-to-AR compared to the phone-only condition. And looking at the subscales, the significant differences in overall scores can mainly be attributed to participants perceiving significantly less effort and less frustration with our approach. This is in accordance with our interview, where participants said that push-to-AR enabled more efficient comparisons and reduce the need to memorize items. Comparisons with phone were in turn described as being more difficult, and participants also indicated that this condition required more scrolling. In terms of performance, our technique significantly reduced the number of interaction steps required to solve the task. So with push-to-AR, participants had to open the card significantly less often. Also, they added and deleted significantly less items to and from the card. Further, we couldn't find a difference in error rate, which is the percentage of wrong items in the card at checkout. However, participants solved the task faster with the phone condition. And we attribute this to participants' higher familiarity with this very common interface, because users already have like a decade or so experience with their phones and touch interfaces. Interesting though, this is not in accordance with participants' subjective experiences. So participants indicated that they perceived push-to-AR as less time-consuming and allowing also for more efficient comparisons. And on the contrary, phone was perceived as being more error-prone and also time-consuming. While this probably indicates that the practical relevance of the difference in task completion time might be limited, we think that once participants get more familiar with AR, this difference will decrease substantially. Yeah, while our results strongly highlight the benefits of enhancing scroll lists on phones with augmented reality, participants also indicated a couple of potential improvements. So for example, participants requested an easy way to delete all AR items with one action, as repeatedly scrolling back to the respective item on screen for deletion slowed them down. And while the stacking feature was seen as necessary to limit the height of the AR list and keep it in the field of view of the HMD, participants also noticed noted issues with occlusion, and they proposed to avoid stacking altogether, reduce the size of AR items, or employ different layout strategies such as a carousel, multiple columns, or just expand more into the AR space. Yeah, and while many participants also positively highlighted the scroll indicators and the quick scrolling, some said that these indicators were too small and hard to tap. And to solve this issue, participants requested to be able to directly interact with the AR items, for example, via mid-air gestures. And this could also help with quickly jumping to items, scrolling through them, deleting them, or adding them to the cart directly via a gesture. Yeah, while push-to-AR already reduces the number of interaction steps, leads to less frustration, requires less effort, and improves user experience, and we are also confident that with further improvements, will also lead to better task completion times. And as push-to-AR is built as a browser extension, it works on almost any web page, giving users a lot of flexibility. So for example, you could use push-to-AR to find a movie to watch, search for interesting web pages, collect research papers, or also decide on a restaurant for dinner. And as participants were enthusiastic about using push-to-AR as part of their daily browsing habits, as soon as HMDs get more comfortable and convenient to wear, We hope to inspire future work on combining phones with augmented reality. And for more details, please refer to our paper. And now I'll happily try to answer your questions and look forward to discussion. Thanks a lot.
Thank you very much. Questions, great. I'm on my way. Is the next one.
Hi, Steve Feiner, Columbia University. Great talk. It's a really cool application. But as you push more and more stuff, you get more and more stuff stacked up. And had you thought about the idea of being able to move stuff from the attached to the phone stack into the environment around the user, kind of like a bulletin board surrounding them?
Yeah, that's a great suggestion. That's also what like a lot of users requested. So just be able to grab the augmentations and put them somewhere into the room. So I think that could be a cool next or future work or extension of our concept. Yeah. The only thing we need to consider then is how do we do like the scroll synchronization. But maybe it could be like that you can detach, but also attach again, so that it fits in again into the scroll list.
Thank you.
Yeah, thanks a lot.
Hi, really cool idea. Did you consider maybe doing a study where you're comparing a standalone app where there's maybe a collapsible or hideable panel with the same idea, same concept as this concept, and you're comparing the same standalone app with an AR app to see, does AR specifically make an enhancement, or is it the novel idea you have of saving items as you scroll in a collapsible panel?
Yeah, that's also a great question. So you're probably like referring to like folding, like the scroll list or things like that. I think that could also be like a cool comparison for future work. But I guess still like the screen space is still limited. So like you can't, like folding works to an extent, but it's not like scalable for a lot of items. And I think there like the AR interface has like an advantage because like referring to the last question, we could even expand more into the AR space. So like use more of the space we have available around us. And I think folding is still like limited to an extent on the small phone screen. Yeah, thanks a lot.
There were two more questions here. I'm not sure who was first. I think it was Doug and somebody else. Sorry.
Thanks, Doug Bowman from Virginia Tech. Awesome talk, and like this is one of those, like you see the video for 2 seconds and you're like, oh, what a great idea. So really nice. My question though is, this like presupposes a future where people have headsets on, but at the same time, the problem you're trying to solve is because of the tiny screen of the phone. And so if I have a headset on, then the phone no longer needs to have a tiny screen. So is this approach viable in an era when we have the ability to display anything, anywhere?
Yeah, that's a great question. I was thinking a lot about this question already when I created this concept. But I think there will be at least a time where both will coexist. So we will have a time where we have phones and we will have headsets, and then like for that time it's of course relevant. But also I think like one advantage the phone has is like the touch input, which is very precise and very accurate. You get the tactile feedback of the surface you're touching on, and I think this is also a benefit we don't necessarily have with just the glasses. At least not now. Maybe someone will come up with some cool feedback or like accurate input methods that like go beyond what we have right now. But yeah, I think that's probably what I would say to this. Yeah.
Thanks. I think to be fair and also respect the break, I would stop here. Please approach the authors after the session. We have a short break now, and then there is in this room 3DUI 2, which is the best one. So just stay here.